Okay, so once again, good afternoon, everyone. So this time, our presenter will be able to discuss about algorithm, no, in clustering. So in mathematics and in computer science, an algorithm is a finite sequence, no, of rigorous, well-mannered, well-defined instruction, typically used to solve a class of specific problems or to perform a computation. So algorithms are used to specifications, no, of performing calculation and data processing. So to give us more details about the topic, let us all welcome our presenter. Go ahead, sir.
So yeah, my name is Joe Madroner and my topic is data mining basic algorithm. An algorithm in data mining or machine learning is a set of heuristic and calculations that creates a model from data. To create a model, the algorithm first analyzes the data you provide, looking for specific types of patterns or trends. The mining model that an algorithm creates from your data can take various forms, including a set of clusters that describe how the cases in a data set are related. A decision tree that predicts an outcome and describes how different criteria affect the outcome. And a mathematical model that forecasts sales. Also a set of rules that describe how products are grouped together in transaction and the probabilities that the products are purchased together. The most popular well-researched methods of deriving patterns from the data is clustering. A cluster of data objects can be treated as one group. While doing cluster analysis, we first partition the set of data into groups based on data similarity and then assign the labels to the group. The main advantage of clustering over classification is that it is adaptable to changes and helps single out useful features that distinguish different groups. Stages of clustering. First, we gather raw data, then apply clustering algorithm, and then the result will be clusters of data. To understand better the result, what is clustering? Let's make an example doing it in customer segmentation. Our goal is to make 3 marketing strategies. We have 2 information, which is age in years and engagement with the page, numbers of times per week or days per week. We look at the potential customer base. So by looking at this list of people, what groups can you come up with? We can take a while and actually take down the list to come up with the groups. But for example, if this person and this person has a similar data, which is almost similar age, and of course the engagement of the pages. So we can take a while and actually take down the list to come up with groups, but there's gonna be some easy way to do this. Let's try to plot it like this. Okay. So in the horizontal axis, we put the age, and in the vertical, we put the engagement to the page, and that's how to do clustering. We group them based on their similarities in their data. These are cluster 1, 2, and 3. That's the overview of how clustering is done. Types of clustering. There are many types of clustering, but right now we will discuss about the 2 common clustering, partitional clustering and hierarchical clustering. So let's first discuss the partitional clustering. These clustering methods used to classify observation within the data. It is set into multiple groups based on their similarity. The algorithm requires the analysis to specify the numbers of clusters to be generated. For example, in partitional clustering, we have an object, and we call it the object, and we will divide it into partitions. Like in like this is our okay, wait. For example, these are data. These are X and Y axis, and these are data. These are data. And we call it the object. And we will divide it into partition. And in eyeballing, we will it seems like we can divide it into 3 partitions. One of the common method or algorithm in partitional clustering is k-means clustering, wherein k is equals to the numbers of clusters, which is we have 3 clusters. So to develop a clustering algorithm, we just give the whole data set to algorithm. And the data set will automatically create this type of cluster. I will just have to supply the value of k, and it will divide it into cluster. So to understand it better, let's try another examples. So let's imagine that we are an owner of a burger store, and we want to place 3 stores in the city. What we are going to do is we will put them in such way that we serve our customers in the best possible way. For example, this is where they live. So what we want to do is to locate a 3 burger store in the best possible way that will serve our customers. So if you look at it, you can come up with 3 places, right? And it seems like we should have a red one. A red one for our red point, and a blue one for our blue point. And also a yellow one for our yellow point. So this is how you do partitional clustering. We partition it in 3 clusters. For a human, it's easy, but for a computer, it has a harder time. So what the computer is gonna do is like in the most machine learning, it will start in a random spot and start getting better and better. To elaborate it more, for example, first it locates 3 random points like this, and puts 3 burger store there. So now what we are gonna do is the series of slightly obvious logical statement that when put together will get us to a better place. So the first logical statement, it seems like if we have a burger store in these places, everyone should go to the closest one to them. That makes sense, right? So we gonna plot all the people that go to the red, to the blue, and to the yellow burger, basically to the one that is closest, like this. These people who lives here is closest to these stores, the red, blue, and yellow. So, and in this, and we will have another logical statement. If all the red people go to the red burger store, it would make sense to put it in the center of all those customers. And the same thing to the blue and yellow burger store. Basically, you will move the burger to the center of the customer that it serves, like this. Then we will just continue the first step again and again. Right now, we adjusted it to the center of the customers. It represents like the data will be changed. Like for example, this data is much closest to blue point. where our blue burger store is. So we will turn it into blue again, and the other one to the yellow because it is close to the yellow point. And uh, uh, let me rephrase it. Wrong explanation again. So we okay, we center the our points, yellow points, blue points, and red points to the center of our customers or data it represents. So as you notice, the the blue data here is closer to the yellow points. So we will turn it into yellow. So this is what it looks like. And of course, the second logical statement, we will move uh, the our burger store in the center of our customers like this. Then right now, as you can see, it happens again. The red data is much closer to the blue data. So we will do it again. We'll turn the red data to the blue and we'll center again the pointers like this. So that's pretty simple, right? And a computer can do it because a computer can find the center of a bunch of points just by averaging the coordinates and can also determine if a point is closer to one another than to other one because it simply just applies the Pythagorean theory or distance formula and can compare numbers. These are decisions that the computer can make very easily. Now you may be noticing that we took one decision that seems to be taken by a human and not by a computer, right? We decided that there were three clusters, but as we said, that's for a computer to decide. As a human can see it, but a computer can't. So here's a question. How do we know how many clusters there? So for this, I have few methods, but I'm gonna show you what we call elbow method. For the elbow method, basically says that try a bunch of numbers and then be a little smart on how to pick the best one. So let's try which one cluster we can do this algorithm. Actually, we could do it only in one cluster. We're probably gonna get something like this. Uh, uh, every house can go to the same burger store. Let's do this with two cluster. Um, and you can start seeing that this algorithm can actually depends on where the original point starts. Sometimes it works, sometimes it doesn't. And also sometimes it gives you different answers. So let's say we try to cluster and we got this. Then try to cluster. We got a solution that we have then. And we try 4, 5, and 6 clusters. So by looking at it, we can see that the best solution is the 3 clusters. But again, we need to teach the computer how to find the three clusters. So we should think like a computer. So we can rationalize things. We have to do things like measuring distances, comparing numbers, averaging coordinates, etc., etc. So with those tools, how we find the three clusters the best is what we need is a measure of how is the clustering, and maybe the following measure will make sense. Basically, we're gonna do is we're gonna think of diameter of clustering, and the diameter is simply gonna be the largest possible distance between 2 points of the same color. That basically tells us how big each group is in a rough way. So let's look at the first one cluster solution. The longest possible distance between 2 points of the same color is this one. Oops. This one. And for the second cluster, this one, third, fourth, fifth, sixth. So we just measure uh, the farthest or the longest distance uh, uh, between datas of the same color, like this one. And what we're going to do next, uh, conceptually, what we are trying to do is define the next method, which is the able method. So what we're gonna do is we take all these distances and we graph them in the best way, the best way, this the following way, like this. So for as you notice, we just these are cluster 1, cluster 2, cluster 3, cluster 4, cluster 5, and so on. We just made a graph, and this is how it represents. And as you could see, that's why it called elbow method. We could see the best cluster by just seeing the corner of this graph. And as you could see, cluster 3 is it represents it best. So there are other way to do the k-means. We can do it in line or heat map. Actually, in a line, imagine you had a data like a data that you could plot on a line. For example, we have data here. And then you needed to put it into 3 clusters. You needed to put into three clusters. In this case, the data make 3 relative obvious clusters, but rather rely on our eyes. Let's see if we can get a computer to identify the same 3 clusters. So there are steps. Step 1, select the number of clusters you want to identify. So these, the K, in K means clustering. In this case, our K is equal to 3. We want to identify 3 clusters. So step 2, randomly select 3 distinct data points. So let's say we put it in here, the red one, and the blue one here, and the other one here. So step 3 measures the distance between the first point and the 3 initial clusters. For example, we will measure the first point, the distance first point to the first cluster point, which kung saan sila mas malapit. So like this. This point is closer in the red one. This one also, this one also. And this point is closer to the blue, and so on. And logically, this also 3 data is closer to the yellow. What happened next is we calculate the mean of each cluster. So we have created three clusters. And we will calculate the mean of each clusters. So what will happen after we calculate the means? There will be generated a new cluster points. Of course, if we compute the mean of our data, I probably will put in the middle of our clusters. So what will happen is like from before, when we do it in a X and Y axis. It's just the same. Then we will do the step one again. We will measure the distance of the first point and second points in which clusters point they are closer. Then we will continue doing it until it no longer be able to move our cluster points. This is the overview of the line measurement in K-means clustering, and of course, in heat map clustering actually, as you can see, there are values. For example, we have only uh, two set of data, X and Y axis. We will just have to put it in X and Y axis. And based on the values, we will place the data and we will do it like what we did before. So that's the overview of partitional clustering. And now we will move on to hierarchical clustering. Hierarchical clustering, now we have, it is another unsupervised machine learning algorithm which is used to group the unlabeled dataset into cluster and also known as hierarchical cluster analysis. In this algorithm, we developed the hierarchical cluster in the form of tree, and this tree-shaped structure is known as dendrogram. Sometimes the result of K-means clustering and hierarchical clustering may look similar, but they both differ depending on how they work, as there is no requirements to predetermine the number of clusters as we did in the K-means algorithm. So we have two techniques, clustering techniques approach. The agglomerative. Agglomerative is a bottom-up approach in which the algorithm starts with taking all the data points as single cluster and merging them until one cluster is left. And the second one is divisive algorithm, is the reverse of the agglomerative. Agglomerative algorithm as it is a top-down approach. So to explain it well, in this topic, we will discuss the agglomerative hierarchical clustering algorithm. For example, these are data. In agglomerative clustering, the approach, at the beginning, how do you explain it? Like, the closest pair of the cluster are merged into a single cluster that contains all the data set. This hierarchy of cluster is represented in the form of dendrogram. So first, we will combine the closest data to each other. For example, like this. This one is closer, and this one to each other. We will group them. This is how agglomerative. Then we will group another cluster which is closer to themselves, and then we will group another one. It's a continuous step, like we will group until it is a single cluster data set. So the next one, we'll group this one and this one. Now we have only 3 clusters, and we will group it, this data. Now we have only 2 clusters, and we will group it into 1 clusters. And this is what we call agglomerative hierarchical clustering. This is the overview of agglomerative hierarchical clustering. And then we will put it into dendrogram, how the agglomerative hierarchical clustering works. For example, these are data. We group them. Let's say this one, this one. Okay. This one, two, two and three, four, five, six, seven, and eight. One, two, three, four, five, six, seven, and eight. This is our distance. So for example, we group one and two. Then we will connect it, one and two, and we will group four and five. Every time we group data, their distance is much longer than the previous one. So the next one, we will group 6 and 7. And then we will group 3, 4, and 5. Oops, wrong. This is wrong. 4 and 5. I hope you understand it. I know my topic, but I'm not good explainer. So yes. So then we will group 6, 7, and 8. And then we will group 1, 2, 3, 4, and 5. And we will group them all. So how many clusters we did before? We have 1, 2, 3, and then second phase became 3, then 2, and became 1. That's how Dendo diagram looks like. Di lang siya presentable, but I hope you understand. So how do we decide the distance of the clusters of numbers? Before we go there, I will explain first the divisive hierarchical clustering works. As I said before, it's just the opposite of agglomerative hierarchical clustering. Like in agglomerative, for example, these are datas. We group a single data into each other, the closest one, until we group them all. But in divisive hierarchical clustering, we have a single data set, and we have one cluster, and we will put clusters inside of it. And for example, like these 3 clusters inside one cluster. For example, this is cluster A, cluster B, C, and D. So the Dendo diagram will be look like this. We have 3 clusters inside cluster A, which is B, C, and D. And of course, in the D clusters, we can group data sets of data. For example, we have E and F. So in D cluster, we have 2 other clusters, E and F. And we can repeat it of how many times cluster do we want, like and so on and so on. So how do we decide the distance or the number of clusters? It's so yeah. So, for example here, deciding the number of cluster, we can cut. I forgot about this. I'm sorry, I forgot about the how to decide the distance or number of clustering. So I will move in the applications of clustering analysis. Clustering analysis is broadly used in many applications as market research, pattern recognition, data analysis, um, and image processing. Also, clustering can also help marketers, and they can characterize their customers groups based on the purchasing and searching patterns. And also in the field of biology, it can be used to derive plants and animals, categorize genes with similar functionalities, and gain insight into structures to population. And clustering also helps in identification of areas of similar land use in Earth's observation database. It also helps in the identification of groups of houses in the city according to the house type, value, and geographic location. Also, clustering helps in classifying documents on the web for information discovery. And also, clustering is also used to outlier detection applications such as detection of credit card fraud. And as a data mining function, cluster analysis serves as tool to gain insight into distribution of data to observe characteristics of each clusters. I hope, classmate, you learned something from me. I do understand my topic, but I'm not a good explainer. So thank you, everyone.
Okay, thank you very much, sir. No, again, as what our presenter discussed, no, actually when it comes to algorithm, no, it started actually since antiquity, no. So arithmetic algorithms such as division algorithm used by ancient Babylonian during that time, no. And we have a lot of algorithms available right now, no, because again, an informal definition could be a set of rules that precisely defines a sequence of operations. That is an algorithm characterizations, no. And of course, when it comes to design, we have a typical steps in the developing of algorithms. So the problem definition, the development of model, specification of algorithm, designing an algorithm, no, checking the correctness of the algorithm, analysis of algorithm, implementing an algorithm, program testing, and the documentation preparation. So therefore, no, let's say if you are in a part that you are required to do your research, no, your thesis, looking forward that your thesis is not software development. What we look at in a computer science student is to have a presentation or at a research, no, on how they will be able to prove something specifically in mathematical concepts or algorithm, no, looking forward, no. Then of course we have a high level description of algorithm, no. So if there are no numbers in the set, then there is no highest number. So we let's say, for example, one of the simplest algorithms is to find the largest number in a list of numbers of random order, no. Way back in our data structure and algorithm subjects, no, we have Euclid's algorithm, no. We have also actually a lot, no, because most commonly, no, testing the Euclid algorithms, no, do that as a few test cases usually give some conditions or even some confidence in the core functionality. But of course, in the Euclid algorithms, just not only testing are not enough, no. So for test cases, one source, no. And we have also an algorithmic analysis, as our presenter mentioned, no? And of course, it is frequent and important to know how much a particular resource, no, is theoretically required for a given algorithm. And when we say for by implementation, we have recursion, no, in data structure. We have logical, we have serial, parallel, or distributed. We have deterministic and non-deterministic algorithm. We have exact and appropriate. And I don't know if you're also aware with the quantum algorithm, no. Then by design paradigm, no, we have also the divide and conquer, search and enumeration. Maybe you've heard also the randomized algorithm, no, reduction of complexity, backtracking. When it comes to optimization problems, no, we have the linear programming, no, dynamic programming. And I don't know if you're also familiar with the greedy method. no, or the greedy algorithm. No? We have also the heuristic method, no, yung optimization problem, heuristic algorithms also. And we have a lot of algorithm actually by field of study, by complexity. We have continuous algorithm, and of course, when it comes to algorithm, we need also to consider some legal issues, no, because algorithms by themselves are not usually patentable, no. So in other country, no, a claim consisting solely of simple manipulation of abstract concept, numbers or signal does not constitute processes, no, and hence algorithm are not patentable, no. However, practical applications of algorithm are sometimes patentable. Let's say, for example, if you still remember about the diamond V there, no, the application of a simple feedback algorithm to aid in the curing of synthetic rubber, no, was deemed patentable. So the patenting of software is highly controversial, and there are highly criticized patents, no, involving algorithms, especially the data compression in such as Unisys LCW patent. No, some cryptographic algorithms have export restriction, no, yung export of cryptography. No, if you still remember the cryptographic algorithm, no, for deciphering encrypted code was developed by, of course, the I don't know if you remember Al-Kindi, no, during the 9th century. He is the Arab mathematicians, no, and what else? So I think that's it, no, for this. We need to accept the fact that algorithmic entities, no, refer to autonomous algorithms that operate without human control or interference. No, recently, no, attention is being given to the idea of algorithmic entities being granted legal personhood. No, then of course the algorithmic synthesis, no, yung high level synthesis na tinatawag natin, sometimes referred as C-synthesis, no, this will be an electronic system level synthesis. No, algorithmic synthesis or behavioral synthesis is an automated design process, no, that takes an abstract behavioral specification of a digital system and find a registered transfer level, no. A while ago, our presenter discussed in a mathematics and a computer science an algorithmic technique, no, which is general approach to implementing a process or computations, no. A while ago, I have mentioned also different list of algorithms, no, and so on. So I think that's it for this topic.